Hi, thank you for joining our talk. A decade after Stuxnet's printer vulnerability, printing is still the stairway to heaven. First, let's introduce ourselves. My name is Peleg Adar. I'm in the InfoSec field for more than 7 years, currently working as a senior security researcher at Saybridge Labs. My main focus is on Windows internals and vulnerability research.
Hi, my name is Tomer Bar. I'm in the InfoSec field for more than 15 years, currently working as a research team leader at Saybridge Labs. My main focus is on APT research, Windows internals, and vulnerability research. In this presentation, we will cover the following. We will demonstrate how a threat actor might have the ability to build the propagation part of Stuxnet 2.0. We will do that by a walkthrough on the vulnerabilities which were used by Stuxnet. For each one, we will describe the root cause, describe the patch, and evaluate the effectiveness of the patch. We will continue with a deep walkthrough of our print spooler research findings, including demos of the 2 0 days. Finally, we will suggest a new mitigation for the entire arbitrary file write bug class. We will be focused on answering 2 fundamental questions. Is it possible to build equivalent propagation capabilities as Stuxnet capabilities? Second question, if I fully patch my entire Windows operating system, am I safe now? Last note before we start. We will use 2 symbols during our presentation. A narrow patch means that the patch logic is very specific and it was possible to re-exploit it. And secondly, a regular patch means that it solves the problem and had not been bypassed until nowadays, as much as we know. Now that we are ready, let's see the recap and the timeline of Stuxnet. Stuxnet is considered by many to be one of the most complex and well-engineered computer worms ever seen. It is believed that the project was developed in 2006 and lasted 4 years until it was discovered. So this is how Hollywood imagines Stuxnet. Actually, I love Hollywood, but in real life, Stuxnet can be described by the following 3 parts. The first part is the propagation to the target network by using 3 remote code execution exploits and 2 local privilege escalation exploits. The next part is the special evasion techniques, which allow Stuxnet to operate under the radar. The third part is the final payload, delivering specifically to Siemens PLC. In our opinion, a decade after Stuxnet, the most interesting part is the propagation capabilities, which is still relevant to almost any targeted attack. Let's zoom into Stuxnet propagation capabilities. We will describe them one by one. Although it was a decade ago, it's still relevant to all of us because according to a research posted in 2017, those capabilities were used widely after Stuxnet for attacking a wide range of organizations. Let's dive deeper. Handing over to Peleg.
Thank you, Tomer. So let's start and talk about the LNK vulnerability, which was used by Stuxnet. It used it to spread via weaponized USB flash drives, traveling between internet-facing computers and internal network computers. So the attack vector contained a crafted LNK file, which is a shortcut file. Once it was displayed, an arbitrary DLL, which was specified as the icon file of the LNK, was executed. Here's a screenshot of a crafted LNK file, which exploited the vulnerability. You can observe that the LNK file contains the following: the path of the CPL external file, and the icon ID, 0, which caused the code to trigger the execution of the DLL every time the LNK file was displayed. So let's take a look at the exploitation path and how it was patched. The main problem was that instead of loading the CPL DLL file as a data-only file by using load library X, the code actually called the load library W function and also executed the DLL. We expected the patch to replace this call in order to avoid execution, but let's see what was actually happened. So the patch added two validations in order to mitigate the vulnerability. First, it checked that the provided CPL file was on Microsoft's whitelist and was allowed to be loaded. Next, the icon ID, which we control, would have been extracted and converted from a string. If the ID was 0, it would override the 0 with -1, meaning it wouldn't be loaded. The patch was very specific, because as you can see, the load library function still existed, meaning that if someone would have been able to bypass the validations, then the CPL could have been executed. So let's see the bypass, which was patched 5 years later. In order to bypass the patch, we need to bypass the icon ID check and transform it to 0. It can be done if you will be able to send the minus sign as a parameter to str to int_w function. Let's see exactly how it was done. Because of a type confusion between a white car buffer and a car buffer, the original icon ID string was truncated. We can exploit it by providing a long enough buffer, so the icon ID will turn into the minus sign. Once str to int will return 0 as the icon ID, our arbitrary CPL will be executed. The patch for this one was pretty simple. The truncation bug was removed. The call to load library, which was the actual root cause, wasn't changed. That means that if there's another way to trigger the load CPL module function, it would have been still vulnerable. And apparently there was. 2 years later, a new vulnerability was discovered and patched. It called the load CPL module function by using another exploitation path, which was left unpatched. So the patch for this one was adding the previous logic of a CPL whitelist. But load library still was not replaced. What's interesting here is that we have noticed that there is another last path to load library function, but we haven't seen any disclosed vulnerability yet. So moving to the next propagation capability, next we will talk about the Stuxnet's RPC vulnerability. Handing over to Tomer.
Thank you, Peter. On 2006, 3 years before Stuxnet's first known infection, a new wormable RPC vulnerability was discovered and patched. According to Microsoft, it was a very limited scope attack back then. But later on, a very similar exploitation path was used by both Stuxnet and Configure Worm, which became one of the most spreadable worm ever seen. RPC vulnerabilities were the main cause of global computer worms since 2003. Remember Blaster? So it's obvious that the cost of a vulnerability in this mechanism is huge. Let's dive into the specific details. The RPC vulnerability root cause that we will present is due to a canonical path. So let's understand what is it, a canonical path. It's actually pretty simple. It gets an absolute path and convert it to the shortest absolute path in the meaning of string length. The most common usage of canonical path is for textual comparison of two different representations of the same canonical path. The original vulnerability was a type confusion, which led to a classic stack-based buffer overflow. The vulnerable function was copying a buffer which exceeded the allocated buffer, causing memory corruption. Here is the exploitation path. An RPC request triggered the vulnerable function remotely, which led to an out-of-bound write caused by WCS cat function. Please notice the RPC function's name, netpw. We will explain why it's important in the following slides. The patch added a proper buffer length check, which eliminated the original buffer overflow vulnerability. 2 years later, a newer vulnerability was discovered in the same exploitation path. This time, it was discovered in the RPC wrapper function, which is called netpr. This function calls the original vulnerable function directly. Remember netpw? Let's dive into the root cause. So the root cause of the vulnerability is that the input path includes more /.// cars than the number of prior directory entries. This will result in gaining control over the output buffer pointer, which will point backwards on the stack and will trigger out-of-bound writing after calling the WCS copy this time. So the patch MS 867 replaced the WCS copy function with a safer function, string copy worker W. Let's dive into Stuxnet task scheduler vulnerability. But first, let's understand how the task scheduler worked. The task scheduler job XML file contains the metadata of a job, including which user will execute the job. The folder which contains it is writable by all users. To protect the integrity of the job configuration files and prevent users from modifying them, task scheduler calculated a CRC32 checksum on each created task XML. When it's time to start the job, task scheduler recalculated the XML checksum and compared it to the original value. If they matched, the job executed. If not, it would have been ignored. The CRC32 algorithm is collision prone, which may lead to data forgery. Stuxnet Zero-Day exploited this fact by forging an XML file of a job which was executed as anti-authority system. It had a custom CRC32 checksum, which was identical to the original task XML. Therefore, it would have been executed as system, resulting in a local privilege escalation. In the patch MS-1092, Microsoft implemented a second integrity check by using the SHA-256 algorithm, implemented by the compute hash function, which is less collision prone. Moving forward, 9 years later, a newer task scheduler vulnerability was found. The vulnerability abused the backward compatibility feature of the task scheduler mechanism, which provides the option of migrating all tasks from C Windows task folder to the new task folder, which is System 32 tasks. In order to exploit it, the attacker would need to perform the following 4 steps. Step 1, create a new job. As a result, an XML file would be created in the new tasks folder. Step 2, override the job file in the legacy task folder with an hard link to the file which the attacker wishes to control. Third step is creating a new legacy task with the same name. And finally, trigger an old-to-new task migration over RPC. As a result, the task scheduler service would update the security information of the file which the attacker wishes to control, granting the attacker full control privileges on it. The attacker can now replace or write to any file, gaining a local privilege escalation. So this is the exploitation path that was used. Let's see how Microsoft patched it. The patch makes sure that the file is not a symbolic link by using 2 different checks. The first check verifies that the original path is the final path of the file. If it's different, it means that it was redirected by a symbolic link. And the second check verified that the number of the file's NTFS links is not bigger than 1. Okay, so let's see the 4th vulnerability, moving over to Win32k. Actually, there were dozens of Win32k local privilege escalation vulnerabilities over the last decade. Here is a list of several options from 2020 which can replace the original already patched vulnerability in order to rebuild the Stuxnet 2.0 propagation capabilities part. The only capability which remained is the print spooler vulnerability. Let's start to talk about our printer spooler research and findings. We will start by presenting how we found a 20-plus-year-old bug by using 20 minutes of fuzzing. We have noticed that each time a print job is being created, it is represented by 2 files. First, an SPL file, which simply contains the data to be printed. Second, an SHD file, shadow file, which will be focused on. It is represented by the undocumented shadow file struct and contains the metadata of the print job. For example, printer name, printer port name, document name, and etc. We found that the printers folder, which contains the SHD files, is writable by all users, and that the SHD files are being processed once the service is started. So we ask ourselves, what will happen if we craft our own SHD file? So we started to mutate the SHD files and fuzz the service. After 20 minutes of fuzzing, we had our first crash. We have managed to crash the print spooler service by using a limited user and a crafted SHD file. It appeared that the code was trying to dereference some part of our data, treating it as a pointer to a security descriptor without any validation or sanitization of the data we provided in the SHD file. Microsoft did not fix this bug. We will show the response in the end of our talk. Okay, demo time. Let's see a demo of the crash in the latest Windows 10 Insider build. So on the left side, Johnny is a limited user. We can see that we are running on the latest Windows 10 fully patched machine. On the right, the user John is administrator, and it is used only for convenience to avoid restarts of the OS. Instead, we'll restart the service to trigger the vulnerability. So we are copying the crafted SHD file to the printer spooler directory. And now we will trigger the vulnerability by restarting the service. And listing the printers via WMI command. As we can see in Procmon, we crash the service. We will copy the SHD file and the SPL file to the printer's spooler folder. And we will use John as an administrator for convenience reasons to avoid OS restart, and instead we will restart the spooler service instead. And after listing the printers, we can see that the service is crashed. Handing over to Ben.
Thank you, Tomer. So the crash was cool, but we wanted more. Let's talk on how we got local privilege escalation twice. One of them is still 0-day. So in order to understand the next vulnerabilities we found, we will dive into the printing process in the Windows OS. The print spooler is the service which is responsible for creating and handling print jobs in the Windows OS. Accessing the print spooler is possible remotely, for example, using a shared printer, and locally. We will focus on the local scenario. More specifically, we will focus on the fact that the spooler allows the user to print to a file by using a virtual printer. This is an important part, which our further slides rely on. A quick brief on the flow of printing to a file scenario. First, a user sends some data to be printed using an application, for example, Notepad, and specifies which file he would like to print to. It means that the data will be printed, which means will be written to a file using a virtual printer instead of printed to a real printer. The spooler service, spoolsv.exe, which is the RPC server, gets the request. Later on, the local print provider, which is responsible for printing data to files, will print the data into the file which was specified by the user. Let's start with the first print spooler vulnerability, which was used in Stuxnet. This is the flow of the vulnerability which was providing a remote code execution. The vulnerability exploited the fact that the spooler allows a user to print to a file on a remote computer on behalf of system, and has printed the malicious file to system32, which was a MOV file. So it was patched on 2010. The patch included two validations. A, check if the printing job was dispatched locally on the machine itself or remotely. If remotely, it will override and ignore any requested file write operation. Second, it will check that the user have write permissions to the path of the file that he wanted to print to before it's writing to it. Moving forward to 2020, we have found a way to bypass the patch locally using almost the same exploitation path. The first check bypass is obvious because we shifted from a remote code execution to a local privilege escalation. The second check needed some work, so let's dive into our print spooler research. We found that a limited user can do some interesting operations without any elevation required by just using PowerShell commands. For example, adding a virtual printer which prints to a local printer port, meaning it will print to a file, and specifying a path of the file which it doesn't have access to. For example, system32. Okay, interesting. So does that mean that a user can just print any data he would like to system32? Let's check. So apparently no, or that's what we thought. As we mentioned before, the MS-1061 patch has added a function which validates if the user can write to the path he asked to print to, which means that the user won't be able to print data to system32. So let's understand how can we bypass it. Every time the print spooler initializes, it processes the SHD files which are waiting to be spooled in the same directory for every user. A limited user can create an SHD file which represents a print job which prints to any path, for example, system32. Once the print spooler restarts, it will process the SHD file without being impersonated or aware of who created the print job. Therefore, it will operate as anti-authority system and will print the data to any file as anti-authority system, resulting with allowing the user to write data to any file on the system and gaining an arbitrary file write and a local privilege escalation. This was actually the bypass of the second patch validation, specifically for the validate output file function. Because the spooler is running as anti-authority system, it has writing permissions to almost every file on the file system, so the check will pass successfully. So let's see a demo of the first local privilege escalation we found in the print spooler. As you can see, we are running under the context of a limited user. We're using a full Windows 10 machine from March, before our vulnerability was patched. We're using Johnny, which is a limited user. So first, we'll use PowerShell in order to do the following stuff. We will add a printer port, which allows us to print to system32. We will add a printer driver, which allows us to create a virtual printer. And finally, we will add a printer, which is using the system32 port. Next, we will use a pre-crafted SHD file, which represents a print job, which prints to system32, and we will use a DLL payload, which we would like to write to system32. We will rename it to SPL, and we will copy it by using our limited user to the spool printers folder in system32, which is writable by all users. Now, before we will restart the VM, I want you to notice that there are only 3 users in the computer, administrator Johnny and John, and that the following file in Windows 32, which names exploited.txt, does not exist. Next, let's restart the VM by our limited user in order to, the print spooler will process our SHD file. Once we are logged in back into Johnny user, the print spooler service will process our SHD file, will treat it as a print job, and will write our file to system32. Next, Windows service will execute our DLL, and as you can see, we have been able to add a new administrator to the computer, and we was able to write a file to system32 named exploited.txt. Now let's verify that we actually added an administrator. We will open a command prompt which is elevated, and we will just log in using our new administrator user. As you can see, the administrators group contains our user. So we've been able to gain local privilege escalation using the print spooler service. So now that we couple them all together, we reach our destination. We have found equivalent capabilities to allegedly build Stuxnet 2.0 propagation pod, but our work is not over yet. After the first vulnerability we found was patched, we've been able to re-exploit it, and we credited with CVE 2020-1337. Microsoft are currently working on a fix, which will be deployed in the upcoming Patch Tuesday. Therefore, we can't release any technical details right now. We will publish it once the patch will be deployed. But let's see a demo. So as you can see, we're running under the context of Johnny, which is a limited user. We're running under a fully patched VM. Under the context of Johnny, we will execute our exploit, which will bypass the patch of CVE 2020-1048. After we crafted our SHD file, we'll copy to the print spooler directory. But first, you can notice that the exploited txt file does not exist and that we have only 3 users as before. Now let's restart the VM. Once it was initialized, we will log in again to our limited user, Johnny. Now, as before, the print spooler will process our SHD file and will print the data to system32, which is our payload, which is a DLL file. Our DLL file will be loaded into an elevated anti-authority system service, and we will gain code execution. Now, let's try and find the exploited.txt file. As you can see, we write the data to system32, and we have been able to add an administrator user once again to the VM. Let's execute a command prompt, which is elevated. And let's log in using our new administrator user. As you can see, we have gained a local privilege escalation and the code execution using the print spooler once again after the first vulnerability was patched. Handing over to Tomer.
Wow, 1337, that's awesome. So going back to our second question, we would like to propose an additional possible solution as a second layer for patching. We believe in a layered security mitigation approach. So we reported to MSRC on each vulnerability we found, but we still believe it's not enough. So we developed a POC for real-time prevention of the attack. The main root cause of the arbitrary file write bug class in the context of local privilege escalation is the fact that a limited user is allowed to write directly to the following location. This is dangerous and can be exploited very easily, and we found that it's actually not really needed for the regular use. Today, we will release a mini-filter driver which restricts any file writes operation by a limited user to some of these locations as a POC. This mitigation proposal is not specific to the spooler's vulnerabilities and can be used as a template for mitigating the arbitrary file write bug class. Please treat the driver as a POC and be careful not to execute it in production system before validating it for false positive. Let's see a demo. Okay, so this time we are running on Windows 10 RS1, an older version without the patch for the vulnerability we were going to use. And as usual, we are running as Johnny, a limited user. Let's make sure that our driver is loaded to memory. And now we'll present that a regular usage of printing is allowed. So our driver will examine the file write of the SPL and SHD file, and will allow it. We can see that there are two files in the printer spooler folder with size which is not 0. And now, let's copy the SHD and SPL file to the printer spooler directly. Now, actually, our driver examined the write and blocked it. You can see that the files have 0 size. Let's demonstrate a task scheduler exploit. This is a public exploit, and we can see that our driver blocked the write. So for Microsoft's response for the spooler's local privilege escalation, the additional vector for CVE 2020-1048 will be addressed in August 2020 as CVE 2020-1337. And for the spooler denial of service, the technique results in a local denial of service, which doesn't meet Microsoft servicing bar for security updates. We would like to give credit for the following people for researching similar areas: Alex UNESCO and Yarden Shafir, Dave Weinstein, IT Hacker, and Jingoa Kia. Today, we release our repository, which includes an exploit POC for CV 2020-1048 and an exploit POC for the 0-day denial of service of the spooler service, the driver for the arbitrary file write mitigation, and in a few days, on August 12, we will release the CVE 2020-1337, the super lit exploit POC. Please check our repository. Thank you for joining us, and let's go over for the Q&A.
So thank you everyone for joining us. We'll take questions now. So first, Jamie Butler asked, do you need to restart the service, or can you just enumerate the print jobs or something? So the answer is, you need to restart the service in order to trigger the vulnerable function. But once you restart the service, you will need to trigger the vulnerable function by, we found a way, we just triggered the RPC request. So you definitely need to restart the service, and then you just found a workaround and enumerate the print jobs. Any more questions?
Yeah, of course, we will provide a link to the driver POC. It's in our SafeBridge repository, GitHub.
We will upload it in a couple of minutes once the presentation will be finished. Any more questions? So Ricardo, the link to the SafeBridge Labs GitHub repository, you can Google SafeBridge Labs. It's the spooler repository, and we will also provide it in the slide itself. And Samuel, the workaround that we found for restarting the service is, of course, just restart the computer. And in the presentation of the crash, in the POC of the crash, we just used a limited and elevated user in order to restart, just to make it faster. But as a limited user, you will just restart the VM.
So there is a question about the false positive that we are seeing in our mini filter. So actually, we haven't seen many false positives, or any, actually, but we haven't tested it a lot in many systems with variant, with multiple settings. So we encourage people to test it, and we believe it will be able to prevent some future zero days.
So Ricardo asked, after this new CD patch, do you foresee a new possible exploit coming out using similar approach? Actually, we don't know. We will wait for the patch to see. So we hope not. And we will make the slides available. We will upload them. Black Hat will upload them at the end of the day, and we will upload them to the GitHub repository as well.
There's about 4 minutes left for you guys to have questions.
So William asked, did the principal print the file as an empty system because he crashed the spooler and it lost track of who the original user was? So it's almost accurate. So the principal doesn't know who sent the printing, who wrote the SHD file, so it works as system, but it does not relate to the fact that we crashed it. The crash was a different POC, and the elevation of privilege was because we restarted the computer. So we didn't know who initiated the print, who pasted the SHD file. So actually, we used a custom fuzzer in order to fuzz the service. Nothing that is already known. We just wrote our own Python script in order to use fuzzer. And would application whitelisting prevent this exploit? Actually, I'm not sure. You understand?
Yeah, but I think that the most important thing is to prevent something that you don't know beforehand. So our driver is taking this approach, and it doesn't need to know which specific vulnerability is being exploited. It just mitigates the root cause. So it's a better approach, I think.
We don't have any plan to publish the custom fuzzer. We will think about it, but we didn't plan to. Can you define what it means to fuzz something? So basically, fuzzing is a very big topic, of course, but in our scenario, we just use something that mutated the SHD file and just use random inputs until we crashed it. Then we started to dive in and understand. So to fuzz is basically to use random inputs and send it to the service. Any more questions? So of course we will publish the GitHub repository on our Twitter, on Sabre Twitter, and on my personal Twitter as well. And it's important to say that we wrote a disclaimer for the driver code. We would like you to read it before you will use it. It's important. Thank you for joining us. Ricardo said, what do you use to modify SHD files? So when we started the research, the SHD file was pretty undocumented. So we reverse engineered the format, and we used the 010 editor in order to understand it very well. And we also added the templates, and we will publish it on GitHub in a few minutes. It's just a struct in C, which we used in this particular editor. What mitigation do you recommend until an official patch is released? So basically, we don't want to disclose anything that is specific that might tell what was the vulnerability. So we just say, let's wait a few days until Microsoft will deploy the patch.
And we're at time, gentlemen.
Okay, thank you very much.
Thank you for joining us.